Now that we know what holds the nucleus together, which is the strong force, and what tries to blow it apart, which is the electromagnetic force, we can come closer to understanding nuclear power. The only current commercial source of nuclear energy, is fission, which is where we split large atoms into smaller ones. For pretty much anything we would consider a heavy element, we can get energy by breaking it into smaller pieces, but we don't want to do it one atom at a time, just like we don't want to have to ignite each molecule of gas in your car with oxygen separately with a separate spark. We want it to be something that will take over on its own. So, what we're looking for are called fissionable materials. If the nucleus is fissionable, when it breaks apart, it's going to release one or more free neutrons, and they can go off and initiate other fissions. So it's kind of like a fire starting the propagation of a reaction. This is called a chain reaction, and it can continue on its own. We don't want it to run away because that's what you do when you make an atomic bomb. We want it to be controlled so that we can use the heat generated to boil water and drive steam turbines, which is just what happens in coal plants and natural gas plants as well. In the US, the only power reactors we have use a mix of two main isotopes of uranium, U-235 and U-238. There are control rods made of materials that absorb neutrons and something that doesn't fission. They keep the reactor operating at the right power level. There's been some discussion of using thorium as radioactive fuel, and there have been some experiments, but nobody in the U.S. has a commercial thorium reactor right now. The advantage would be it's more prevalent than uranium, and it can be designed so that it's inherently safe. The big deal that people are working on in nuclear energy, as far as new stuff, is controlled fusion. Fusion is when you take two small nuclei, which are usually things like hydrogen, helium, lithium, and smash them together to make larger ones. The problem here is we don't get a chain reaction the same way we would in fission. The repulsion between the positively charged nuclei, as we get them closer and closer together, the repulsive force gets larger and larger, and the strong force won't turn on and catch them until the nuclei are touching. The only way we can do this is slam them together at high speed, and we can't slam them together at high speed one at a time. We have to use heat to do that. This is the reaction that powers the sun, but the sun has the advantage of a ridiculous amount of mass to hold everything in place with gravity. It will heat up on its own because it's confined to that small region. But for us here on Earth, without that ability, we need temperatures around 100 million Kelvin, which is hotter than the core of the sun. There's no material that could hold anything like that. Everything would melt way before that. So the two competing ways to try and get this to work now, one is inertial confinement, where this just means we have things happen so fast there's no time for it to spread out and cool off. The other thing is magnetic bottles. So we use magnetic fields to hold these charged particles without connecting them to anything material so they'll lose heat. Now, fusion's been used in hydrogen bombs for more than 60 years, but people have been working at least that long trying to solve the problem of controlled fusion. It may actually happen in your lifetime. The advantages are huge. It's inherently safe, meaning the worst thing that can happen is that the power goes out. You don't have a possibility of a runaway reaction or anything like that. There's very little radioactive waste produced. Most of it was short half-lives, so you don't have to hold on to it long before it's inert. And finally, it uses what's basically water for fuel, so you've got an awful lot there. You might wonder, could we connect, if we get a fusion reactor in the future, could we connect it to a fission reactor and just have the waste product of one work as the fuel for the other? And you can't, which you probably expect because of conservation of energy and thermodynamics and all. But the reason we can't do it in particular is for heavier atoms, it takes more energy to push them together than you would get when they join together. Same way, it takes more energy than you would get back to try and split a small nucleus. In this plot, we have what's called the binding energy per nucleon as a function of nuclear mass. So this tells us the energy we would expect to need or to get if we wanted to add or subtract a proton or a neutron to a nucleus. And we see that somewhere around nickel, iron, right around there, we're at the absolute peak. So anything we do to this, whether we split it or whether we try and fuse it with something else, it's going to take more energy than it gives back. So we're not going to be able to cross that point and still generate energy. We only are going to use small nuclei for fusion, large nuclei for fission, and we won't be able to mix the processes.